Hi everybody. Wanted to give you a brief overview of drawing in Java. This is based in what's known as an abstract window toolkit, which gives us graphics coordinates that have an origin in the upper left hand corner. We base all of our drawing in an area of the component inside of the abstract window toolkit's container, which could be a panel or frame, and we use that component's invocation by the abstract window toolkit's damage control manager of the so-called paint method. And so what we do is provide an implementation for the paint method, and it is called with an instance of an implementation of the graphics context, and the graphics context is an abstract class which you can subclass. You get to draw lines, arcs, circles, many different primitive two-dimensional data types using a integer-based coordinate system. The integer coordinates are supposed to be based inside of actual pixels that will be displayed on the screen. The shapes that you get for the integer coordinate system are relatively limited. You can have fill shapes and outline shapes. When they're outline shapes, they call them draw shapes, and naturally when they're fill shapes, they call them fill shapes. So fill oval and fill rectangle. If you want to draw a circle, you make the oval height and width the same. Same thing if we're drawing a square, you make the rectangle height and width the same. Typically when you draw, you need a color. Colors are often set by default, but if you want the foreground color to be special, you can just call g.setColor, where g is an instance of the graphics context. So now you've got a mechanism for drawing different simple shapes in Java's abstract window toolkit. Don't call paint yourself. Let the abstract window toolkit's damage control manager invoke the thread that calls the paint method. That way, if windows are partially occluded, the paint method can be invoked and only part of the window needs to be repainted. You can call the repaint method, and you could also call it with an argument which is given in milliseconds. So then the question becomes, all right, so what is this damage control manager, and when does it invoke the repaint method? And resizes, exposures, relaying out the component, a show or a hide, anything that inside the component that demands a repaint. And usually you can give a coordinate system for the repaint, which involves a rectangle. So you give the upper left-hand corner of the rectangle x and y, and the width and height of the rectangle. And it extends downward, so the origin's in the upper left-hand corner. So the damage control manager is a thread, and it runs inside of the Windows system, invoking the repaint method and the update for a component. And because Windows have dimension, you can call w.getSize, which returns a class instance called dimension d, and it'll have width and height. It'll also have an x and a y. So the x and y location is in the upper left corner. The width and height is going to be d.w and d.h. When you get the location, you'll be able to get the x and y position. And when the layout manager comes along, it's going to set the location and dimension. So JPanel is a swing component, and a lot of times what happens is paint component is what you use for implementing the low-level two-dimensional graphics. So instead of calling paint, as in the Abstract Window Toolkit under Swing, you call paint, or you have the Damage Control Manager call paint component. And so your implementation should be paint component, not paint when you're in Swing. So if you're going to write custom paint code, you should probably think about calling super.paint. In this way, anything that's been painted by superclasses after you've done some subclassing will get painted. Coordinates go from 0, 0 to width -1, comma, width minus height -1, so you're actually off by 1 pixel. It's not exactly width and height. And that's because we're numbering starting at 0. The border sizes typically are a pixel at the top left and a pixel at the bottom right. And then there are these things called insets. And we'll have insets for every component. And you can have insets for a button, for example, so that a string can have a comfortable border before it gets next to the edges of the button. So the button's text appearance won't collide with the curve inside of the button. So now that you know a little bit more about repaint, I think it might make sense for us to talk a little bit about what it is you can paint. In general, you can have buttons that paint themselves and can paint interesting pictures. You can have them draw images so that you can have icons for your buttons. You can have a variety of different graphics which you can use, and everybody should be able to do some elementary painting. So the question then becomes, all right, how do I paint something that isn't necessarily given to me in the graphics context? Well, you can paint things on a pixel-by-pixel basis using a variety of mathematical models for the graphic object that you want to paint. You can use two basic descriptions of these models. One is called the implicit formula, which is typical. This is where you have the centered circle, x sub c, y sub c is a circle center. So you have x minus x sub c squared plus y minus y sub c squared equals r squared. But if you solve for that formula, you get a square root, which gives you plus and minus, which is the top half and bottom half of the circle. It's a bit awkward for the computer, so when you want to formulate something, try and use a parametric formula with a dummy variable. Here the dummy variable might go from 0 to 2 pi, and now this will give you all the x and y coordinates. Here's a dummy variable that goes from 0 to 1. This is called a parameter that dilates. When t is equal to 0, we'll have all p0. When t is equal to 1, we'll have all p1. And p0 and p1 can essentially be a vector. Here it could be x and y. The implicit formula, y equals mx plus b, has no limit. It's a line that goes to infinity. And so we're actually this is a little bit awkward, because what happens if m is equal to 1 over 0? What if you have a vertical line? So then it looks as though this is not a well-posed mechanism for defining a line. So what we like to do is we like to come up with a mechanism that will be well-posed under all circumstances. This will generate, f of t will generate a line segment. And the line segment can be used to cause smooth dilation between any two parameters. It could involve colors in three-dimensional space or points in 3D space. But here we're just using points in 2D space, and we can see when we multiply these things out, you can get a much more efficient formulation. And so now we have this thing here called the draw test. And this is interesting because what it enables us to do is to draw a line and then fire a ray, and then we can model the bouncing of the ray around inside the circle and essentially trace the ray as though the circle were an optical piece. And here we can model a plano convex lens, and here we can put in coordinates of the center. We can throw in some strings, and in fact we have the ability to model a whole bunch of different interesting and wonderful graphic objects. We can also do some basic business graphics. Here's a stock price once every 30 seconds or so. We can model something like the stock as it changes. We can draw a string using an X and Y location, but then the question becomes, what kind of font will the string use? And so now we have to get into a discussion about font metrics. And maybe we'd like to change the color as well. Fonts have lots of attributes. And so when you go into the graphics context, you can set the font. And then when you do, you're going to need to know something about the font metrics. Once you get involved with that, you go to the next generation of the graphics context called Graphics 2D. And this takes you into a floating point graphics coordinate system. So this is a font definition. You can say new font, and you can put in the font name, throw in the style such as bold, italic, and plain, and then you can put in the size of the font, and that size is typically given in points. Point is 1/72 of an inch. The arc gives us a top left, top left for X and Y, and then a width and height. And then we have a start angle and an arc angle. And so you can do an outline and arc, or you can do a filled arc. Rectangles also work with a top left, but they give you a width and a height. And a round rectangle, we have exhibits of that back in here. You can have outlines or fills. The filled rectangles with their color are set with a color that's done with a G.set color. And we've seen the filled rectangles work just like rounded rectangles, and you have to give the same parameters, the arc width and height. You can actually take an instance of an image, and then you can get the graphics context off the image instance and start to draw right on top of the image. That'll give you the ability to do an overlay. And you can also create a blank image and then just start to draw on that. You can draw on it with any color pixel you like. So for example, here we made an image and then we started to draw on that. And you can save the image in a variety of different formats using API that's provided by the book code. And so then comes the question, should I be using bitmapped versus vector graphics? And if you want your lines to come out nice and smooth on a PostScript printer or a high-resolution device like a laser cutter, then it's better if you use vector graphics. If you start using bitmapped graphics, your laser cutter will be able to produce the line, but it's going to have some jaggies in it. It won't be a smooth line. And laser printers also will have these issues. Plus, you're not going to be able to scale things smoothly to different sizes if you don't use vector graphics. If you want to, you can take advantage of the color. There's 24 bits per pixel typically. They call that direct color, with a 32-bit overall depth. 8 bits are reserved for the overlay plane, or what they call alpha. The ability to do 24 bits worth of color, that's 8 bits for red, green, and blue, gives you 2 to the 24 or 16 million different possible colors. If you use fewer colors, you can start to see changes as you move from one color to the next, and that modeling can occur and be easily detected by the eye. So you have a color quantization step function. So here's an example where we draw a series of different filled rectangles at different colors. So we make a new color using red, green, and blue colors, and then we set the color and we fill the rectangle, and that gives us increasingly large numbers of rectangles with different colors with steps that you can see. So once you get involved with Java 2D, you're going to start being able to draw things with the geometric shapes in the java.awt-geom package, and those shapes will allow you to draw very similar objects, only using floating point precision. You'll get the ability to do advanced drawing with cubic curves. These higher order cubic Hermite polynomials include things like Ferguson curves and Bezier curves, and we talk a little bit more about that in some of the graphics courses. And so there's a way in which you can get a demo using Java Network Launch Protocol or WebStart, and I think we can detour into that. But before we do this demo, I think what we'll do is we'll take a little bit of a break and we'll come back with our next video. Thank you.